Hello, this is Videolog entry 199, 199, yes, definitely 199, 191, and it's about noon. Uh, I just recently got a new shirt. This is what I'm wearing right now. Um, it's Maxwell's Equations, if anybody knows about that. Um, it's kind of cool, I guess. I thought it was kind of funny because, in Genesis, when he said, and God said, let there be light or something. Oh, shit. Is that what it says on there? Yeah, and then there was light or whatever, let there be light, whatever he said in Genesis, the first book of the Bible. It's kind of a nice enmeshment of physics and God and Christianity. So I decided to get this. This guy right here is, if I remember correctly, I think that's Gauss's law. D is actually, it's funny because I don't remember them representing it that way, but it's actually, I remember the del operator over the energy of, uh, or the electric field is equal to rho, which is, I believe, the energy density of a given um, field divided by epsilon naught, which is epsilon naught is actually a constant. I believe that's like the permittivity of space. Actually, I think that's epsilon, not an epsilon naught, but mu naught. Mu naught is the permittivity of space, and I think that's epsilon naught is actually the electric something. I don't remember. Uh, so yeah, I thought it was interesting, and so this one right here is, I believe, magnetic dipoles. If you ever taken a physics course, magnetic dipole is just, or sorry, monopole is considered to be zero because if you have like an electron which is moving and it's creating a magnetic field around it. Usually, um, when you envision the magnetic field being induced by the electric field, it's always perpendicular to the electric field. So if you think of like an electron going through space, there's so you also have to keep in mind that there's always, for there to be in a magnetic field, there has to be an electric changing electric field, which is the third one in this equation. Um, if, as you can see, we have a changing electric field with respect the operators with respect to space itself, 3D space, x, y, and t, z, along the electric field is equal to the change of the magnetic field over time, which is basically saying that except it's negated, which is a negative del over del t with respect to the the magnetic field. So you have to keep that in mind. The thing is, like, you can actually rederive it through this equation to get the del operator on the magnetic field, which is equal to zero. If you take the integral of this with respect to t, you get b by itself, and then you would have a del. You have the integral on the other side with respect to the del operators. So the thing is, like, you're doing integral a ddt of uh, uh, a purely spatial uh, object or a function or whatever. So if you take the integral of a constant, then you get a constant, like, or you get a variable, which is equal to, it's a linear variable. Um, so basically, if you take an integral of a quote unquote constant with respect to time, then you'd get just like a linear object. So if you get a linear object and you have b on the other side, you take the del operator again on a constant, then you would get zero. So, sorry, a variable, which is going to be a constant. So the reason why I don't understand how it would be zero in this equation, because well, a constant, if you take the if you differentiate the constant, then, or the variable, sorry, it's a variable. I keep saying constant. Well, actually, now that I think of it, how would this work out? Hmm. Yeah, I mean, it's a constant with respect to time, so I'm assuming if you take the integral with respect to time of a constant with respect to time, then obviously you should get it would spit out t in that equation. So I think that's the reason why it's actually considered to be zero, because if you take the del operator of a t, which is a constant with respect to space, um, that means you would get zero on the other end, because you're looking at the um, the change of that given object with respect to space as opposed to time, but the only variable is time. So if it's constant with respect to time, to space, and you take you take the holy shit, the derivative of that, then you get zero, which is why you have zero on the the right side. It took me a second to say that. So yeah, it's kind of interesting. You can rederive all these equations by just knowing this law here. I think you can rederive that one through this law. I mean, this is Gauss's law, so it's kind of interesting. But yeah, and then you have that guy right there, which is kind of a monstrosity. And I think that's like I think it's called the Ampere-Maxwell law. I forgot how to rederive that one. I think you can derive it from, the electromagnetic partial differential equation for that. But yeah, so that's kind of interesting. Um, yeah, so I don't like the fact that in this one they use like d, which is just e over epsilon naught for d, and then we have j down there. I believe j is the current density or something, and I would have to look at the specifics of that. And again, that's e over epsilon naught for d, and then you have h on the other side of the equation, which is I forgot to be honest with you. Um, yeah, I mean, I think they're all derived through the magnetic and electric field though, so you can find all those answers. But um, yeah, it's kind of cool, I guess. You can look at. I just love the fact that you can rederive the monopole equation through Ampere's law right over here, or yeah, not Ampere's law. I keep saying Ampere's. It's Faraday's law. This one is Faraday's law. You have Gauss's law here, and then you have the monopole equation. The reason why they call it a monopole is because, again, like I think I was just talking about it, that if you have an electron going through space, right? Um, I guess if you want to look at the equation here, sorry, this side of the equation is an electron going through space. You're just looking at the change of space over this equation here. It induces a magnetic field with respect to time, though, as opposed to it changing with respect to space, which is a little bit weird because space and time are related to each other in physics, obviously. So that's why you get that. The reason now I don't know what experimentation would be best for that. Um, the one that I knew of is when they had they had a magnet. Did they have a magnet? Yeah, I think it was a magnet going through this coil. So if you drop the magnet, it'll eventually stop because this coil is creating a current, right? So then this current creates a magnetic field going up. So eventually it'll just like hover in um, that coil because the reason behind that is because when it induces again, you can look at this equation again and say, okay, so we have a moving magnet, therefore we have a change of the magnetic field with respect to time here. You can take the negative and just say, oh, then that means there must be a changing electric field with respect to space, which is happening in the coil. So there's actually a current going through. You can think of it as that because if there's a current, then of course there has to be a changing electric field, because you can think of electrons moving through this copper wire. So if these electrons are moving through a copper wire, then it's that's a change of charge, right? So you can think of it like that. There are a lot of ways to think of it, but it induces an acceleration in a peak acceleration to a velocity, a max velocity for it to go through the current, through the wire, and then if that's happening, then it's also going to be inducing its own magnetic field, which would be going the opposite way, which is also very interesting, because you could think of it like that. So if it has a negative electric field, then it's going to create a negative ddt with respect to B. Now, I think eventually as the magnet accelerates to a certain speed, it creates enough of a opposing magnetic field to keep it floating in space, if that kind of makes sense. Yeah, so... Or does it float actually? No, I think I'm wrong. It stops it from accelerating is what I meant to say, is that it'll reach a constant velocity. It doesn't actually float. which would be interesting. I don't think that would be possible. Yeah, because then of course you had to think about there would have to be an opposing. I don't know actually. Is I maybe I'm wrong. I thought I saw. I think it was an experiment where there was like a floating magnet where you drop a coil through or drop a magnet through a coil and it floats there after it reaches a certain inflection point because again like I mentioned is that um, when you're it creates an opposing like deceleration would be a good word. Deceleration in the opposing direction because it induces a force, which is from the magnetic field, which is, a force is it's, if you ever taken physics before, F is equal to ma. Of course, you could think of it like that, or like the change of momentum with respect to time. So eventually, yeah, you can actually, I think you can get it just float there in that coil just because of that. Um, just interesting. Now, actually, I think there would be a point where it would hit zero for a second, and then you'd still have gravity applying to it, and then so actually it would slow down and then accelerate again. So it doesn't like actually float now that I think of it. So I don't know what I'm saying. I haven't taken physics in a long time, and I got this shirt, and I thought it was interesting. I'm not sure if I'm gonna post this video though. Yeah. But aside from that, I tried posting yesterday and then on Friday and then on Saturday, but I don't know, I just haven't been feeling it, and I'm also still not feeling it today. I've been relaxing, and I don't know. I have a few bad habits here and there that I should be focusing on fixing because it's been nullifying my productivity quite a bit. So I may get back to just having a good and healthy routine. I don't know. I just haven't had the time to really care about being healthy right now. Yeah. I don't know. I just don't feel like talking right now. I just don't feel like talking. That's interesting. Hmm. Okay.